I've had many requests to do a video on a mega mechanism to help you understand it for your tests. This would be part 1 of MegaMechanism1. We are starting with an aldehyde, reacting it with a dithiol in the presence of toluene sulfonic acid using a Dean-Stark trap, which I would like to remind you assists all condensation reactions, in particular the dehydration step. You are making a thioacetal, also known as a dithiane, a dithiane has a pKa of 30 on this hydrogen right here. That's a new one. If you deprotonate the dithiane with sodium hydride, you will make a carbanion here, which will participate in an SN2 reaction with benzyl chloride, thus creating this carbon-carbon bond right here. Sulfuric acid in an aqueous environment will deprotect the dithiane. You will notice I just corrected the dithiane here and here. The sulfurs were in the wrong position on the top. Sulfuric acid in water will deprotect the dithiane, thus giving you your carbonyl back, this time in the form of a ketone. Also, in the last step, the conditions will always also meet the requirements for an alkene to undergo acid-catalyzed hydration to a secondary alcohol. In order for you to start making a bond from sulfur to the carbonyl carbon, you must first activate the carbonyl towards nucleophilic attack. Carbonyls are not typically reactive towards moderate or weak nucleophiles. The mechanism goes thus: protonation using toluene sulfonic acid will give the resulting product. The protonated carbonyl is now reactive towards the thiol, which will attack, and the pi bond will break, creating this intermediate. The sulfonium will be neutralized by toluene sulfonate ion, creating the next intermediate. This combination here is halfway to the thioacetal. It is called a hemithioacetal. In order to make the second bond from sulfur to carbonyl, you must be in a situation similar to here, where you made the first bond from sulfur to carbonyl. You need an activated carbonyl. This situation can be created by eliminating water, creating a second carbonyl double bond to, in this case, sulfur with a plus charge. We must eliminate water. A little too curvy there. Creating this next intermediate. As you can see, you have an activated sulfinium ion, which was very much like the activated carbonyl. Now you can attack it with the sulfur. This is an intramolecular attack this time. creating this next intermediate. During your elimination step, you created a toluene sulfonate ion, which can neutralize this sulfonium, which, if you look carefully, is the conjugate acid of our final product. A simple neutralization step is necessary to regenerate your catalyst and give you your final thioacetal for this first step. Next, we have to deprotonate this acid of the dithiane, which has a pKa of 30. This can be accomplished using hydride ion. Notice I crossed off the sodium spectator. You'll be creating a carban ion right here. Next up, we're going to do a SN2 reaction on benzyl chloride, which creates the product indicated right here. Clearly, to get to our deprotonated ketone product, we must start making bonds from oxygen to the carbon that is right here. Remember, when making bonds from this carbon to either oxygen or sulfur, you need to be in this form or in this form down here. You must have a double bond from the heteroatom to the carbon. This can be accomplished here by doing an elimination of the thiol using an acid catalyst to produce this intermediate here. You have an activated carbonyl here, thiocarbonyl, which can be attacked by water, which is present in all aqueous situations. Water attacks the activated carbon. Not happy with that arrow. Pi bond breaks, neutralizing sulfur, creating this next intermediate here. The created oxonium species is neutralized using this mechanism here. Creating this next intermediate here. Combined with the sulfuric acid created, the intermediate is going to undergo acid-catalyzed dehydration using the acid-base conjugate pair indicated here. Base, as always, grabs the H. Sigma becomes pi, in this case creating a carbonyl. Leaving group leaves only upon protonation to make it a better leaving group. And you have your ketone right here. Notice this leaves you with the dithiol that we started with at the beginning of the synthesis. And your ketone. And your last step involves acid-catalyzed hydration of this alkene, which is a very old mechanism that we learned in Chapter 6. Starts off with protonation of the alkene to make a more substituted, oh, would you not like that arrow? Secondary carbocation right here. Nucleophilic attack by the lone pair on water to the secondary cation will yield this intermediate here. This is the conjugate acid of the final product. The sulfate ion created in the previous step would neutralize the oxonium with this mechanism here. Thus completing our overall process to give the ketone and secondary alcohol, which we will use in MegaMechanism1 Part 2. In summary, to convert an aldehyde to a thioacetal, also known as a dithiane, you must first protonate the carbonyl using sulfuric acid or toluene sulfonic acid, illustrated here. Then attack with an alcohol or a thiol, illustrated here, to make a sulfonium ion, which must be neutralized using the conjugate base of your acid catalyst. The hemithioacetal is then dehydrated using the catalyst's acid once again. An activated carbon double bond to sulfur with a plus is attacked by the thiol, the second thiol, which is neutralized by the conjugate base of the strong acid to give the thioacetal. A thioacetal from an aldehyde has a pKa of 30. It can be deprotonated using a strong base. This generates a carbanion nucleophile, which can undergo an SN2 reaction with a suitable electrophile, yielding a new carbon-carbon bond right there. Deprotection of thioacetals and acetals is accomplished using sulfuric acid and water, or toluene sulfonic acid over here, and water. First step is to create an activated carbonyl by eliminating the thiol from here. There's the thiol. Attack using water to create an oxonium, which must be neutralized using the conjugate base of the strong acid. Then we have acid catalyzed dehydration, yielding the dithiol. There is your deprotected carbonyl. The last step in this process is the acid catalyzed hydration of an alkene using sulfuric acid, which was present from the beginning, and water. Water attacking the more substituted secondary carbocation, creating an oxonium, which is neutralized using the conjugate base of the acid to give the requisite secondary alcohol. Congratulations, this is the first part of MegaMechanism 1, to be continued.